let's introduce the next speaker. It's Daniel Lee. He's calling in from New York. It's very early there right now, I believe. And he is one of the original Stan developers, which you may know is the C++ library for inference and posterior sampling. And it's one of the NumFOCUS sponsored projects, so we're very happy to have him here. Welcome, Daniel. He is also right now the co-founder and CTO of Generable, which is attempting to estimate treatment effects for cancer patients. So, Daniel, I'll let you take the floor.
This is the outline. So I'm going to talk about why Stan exists, when it's useful, and why I use it. Thanks for being here. A quick intro to who I am. I've been a Stan developer since 2011. So that's, since the very beginning of the project. I'd consider myself a Bayesian statistician. In the past, I've been a software engineer working on operations research type of projects. And something that's kind of unique is I've been working on something Stan related pretty much every week for the last 9 years. I'm also a co-founder of Generable, and we, as mentioned, we estimate efficacy of oncology treatments from early phase data. The interesting thing here is that we actually use Stan for our analysis. I'll start with why Stan exists, and I'll start with the motivating problem. This was from 2009. I used to work with Andrew Gelman, and from 2009 to 2017. And the problem here is that we want to estimate public opinion from polling data. So what polling data is you'd get a sample of people, and oftentimes the polls report weighted samples. You get demographic information, age, income, state, all sorts of other things. And then you get responses to questions, yes and no. And the whole point here is to estimate whether or not, in this case, who in the United States supports healthcare reform. The statistical model here is not something super complicated. It's just logistic regression. I'm being a little sloppy here with the notation, so please forgive me. What's important is that inside this X, for each patient I, or sorry, each person I, we know something about their age, their sex, their income, their state, and we have a bunch of covariates there. So that's all and good. That's easy. We can do that using other software. But there's more that we want to do with this. The thing that we actually want to do is hierarchical logistic regression. And what I mean by that is that the data itself comes in hierarchies, inside structures. And we often want to estimate what ML people usually call hyperparameters. And we can imagine that there's a state effect average and a state effect standard deviation. The first thing we should ask is, does that seem reasonable as a modeling assumption? There are 50 states. There's got to be some sense of average and variation, right? Like, seems reasonable. So let's go and estimate it. The first thing you've got to know about that is that maximum likelihood actually doesn't work. You end up with a mathematically degenerate solution. The optimum, if you try to do this particular model, is when the variance is exactly zero. Not close to zero, exactly zero. And mathematically, adding regularization doesn't change the optimum. You can try it out, you can work out the math, you can do it in simulation. You'll just find out that when you do maximum likelihood, turns out that when all the states are exactly the same, you end up with the best solution, which is against the modeling principle that we had. So how do we do this? It turns out that Bayesian inference works, and we can estimate the standard deviation from the data. It ends up being close to zero, like the maximum, but not exactly. And the distribution of these estimates actually capture our uncertainty. But wait, there's more. This isn't the only thing we want to do. We want to add much more to our statistical model. We know that age is continuous. It's not a bend like in this graph here. It's been from 1825 or 18 to 29. States are in regions. So, the Western states are in the West region, so on and so forth. So we kind of have an idea that there's a spatial relationship. We have to deal with missing data, censored data, truncated data, bad data, just all sorts of problems. We know that income is correlated with age. There are very few people that are very young that make a ton of money. That's just how it works. And we can go on and on. So we actually need more flexibility. So this is the motivating problem. When Stan first came about, we were trying to do these political polling models, and we wanted to do hierarchical models and continue to increase the complexity of our models. So next, I'm going to describe what Stan is. Stan's actually a combination of three things. These three things together make up Stan. It's the language, algorithms, and interfaces. So the first thing is it's a language for statistical models. So the goal here is to specify a statistical model. We start with the data, X. This could be multivariate, it could be a time series, it could be anything, but we're just going to call it X. And we want to estimate some set of parameters. These parameters tell us something about the world. And how we link these two together is a model, P. We treat that as a probability distribution function, so that's why we call it P. But it's a function that links parameters to data. If you just intuitively think about it, good values of parameters ends up with a higher P, bad values of parameters ends up with a lower P. Just for some technical details, Stan itself is its own language. It has its own grammar, syntax. It's statically typed and imperative. And users define programs. So they're defining data, they're defining parameters, and they're defining this model, which is the log joint probability distribution function. And the flexibility of this language is that you can write any differentiable joint probability distribution function over the data and parameters, and that's the whole point. So as a quick example, this is logistic regression. And as I mentioned, you can kind of see that there's data here. There's parameters in the second block. Sorry about that. Back. There's data, which is N is the number of data points. You have an X and you have Y. You have parameters, alpha and beta. These are the two things that we want to estimate. And this model statement is a statistical model saying that each observation Y, which is either 1 or 0, is related by this logistic function, logit, of alpha plus beta times X. So this is how you would code logistic regression in Stan. And so what we get is that the users are defining the statistical model. It can be as complicated as they want. It can be very simple. But that's what the purpose of the language is. Next, we have the inference algorithms. So the definition of the model doesn't tell you what inference algorithm to use. In Stan, there are actually 3 different classes of inference algorithms. There's Bayesian inference, there's approximate Bayesian inference, and optimization. And just to get into some detail, in Bayesian inference, the goal is to estimate the distribution of your unknown parameters given the data you've seen. So that means that we're going to approximate that with theta parentheses 1 is actually one set of thetas. So if theta is 1,000 dimensional, we have 1,000 dimensional draw. Then we have a second one, and we keep doing that again and again. And this represents the uncertainty we have around this theta parameter. The second type of inference that people use is approximate Bayesian inference. In our case, this is ADVI, automatic differentiation variational inference. It's an automatic scheme for doing variational inference. And that, instead of solving the actual problem that we give, so we want to estimate we want to estimate this. Instead of that, we're going to find a function that looks close enough to this. And that's what we're doing. You can read the math somewhere else. And then the third thing that Stan can also do is actually try to find the optimum. So we want to find the best value of theta for this function here and return it. And if you recall, doing this over hierarchical models ends up with degenerate solutions. So this is why, as soon as we start building models, we tend to use Bayesian inference because oftentimes it ends up being hierarchical by our modeling assumptions. The third thing that ties Stan all together are interfaces. And by interfaces, we're talking about things that can run Stan. So Stan is its own language, and these algorithms exist. And most of it's written in C++, but we have to run it somehow. So in Python, there's PyStan and CommandStan. If you're in R, Julia, command line, MATLAB, there's a bunch of different interfaces that you can use. So if you have colleagues elsewhere working with other tools, that's not a problem. In a sense, the Stan language, you can hand that program over to someone else in a different language and they can use it. There's also a C++ API if you wanted to use that. There's an automatic differentiation library in C++. And then there are downstream tools from Stan, including RStan ARM, BRMS, Profit you may have heard of. It's by Facebook and it does time series pretty nicely. All right, so now that I've described a little about what Stan is and why it started, I'll talk to you about when it's useful. So there's a sweet spot, and it starts with off-the-shelf packages don't encode your model. So this is when your favorite GLM package, your favorite logistic regression package, I guess that's a GLM, but whenever you do that, a time series package like Profit, when that stops being able to encode the statistical model you want, that's when you start. You also want knowledge of your data generating process. By that, I mean, something about how your data was generated, and you're going to translate that into statistical model assumptions. If you don't have that, it's really tough to use Stan. The next thing you really want is you tend to have a model that is complicated and often hierarchical because you want to use information about the group to inform what you know about individuals, and custom. Custom in the sense that, even if you work with time series data, the package you use might not have truncation and censoring, might only have one of those, might not have particular nuances that you have in your data. And it turns out like it's really good when data is relatively small, relatively meaning relative to the complexity of your model. So if you want to do, so for example, if you have 1 million data points and 2 parameters, that's really easy. But if you have 1,000 parameters and 100 data points, that's really hard to do. And that's sort of when you start using more modeling assumptions and statistical modeling. And that's when you can use Stan. The last thing that Stan's really good for is when you want interpretability. Since this is a statistical modeling language and it's a program and you're specifying it with the program, you can actually go and tell someone what that is. With that said, there are difficulties with using Stan, and I should be honest and tell you these things. The first thing is modeling. Not all models match data. So you can try to fit a logistic regression to non-logistic data, and it's going to fail to produce good output in Stan. That leads to computation and new diagnostics. There are new diagnostics in Stan that even the MCMC community haven't caught up with. Turns out the algorithms that we've developed in Stan far surpass the last generation of algorithms. And that leads to new information that we can use to tell us when there are problems. You also need some skills to use Stan really well. You need to be able to program in Stan, which is yet another language. So if you're already comfortable in Python, why would you pick up another language? There's some learning curve there. And also, once you get used to the basic syntax of Stan, there's actually a little bit of a leaky abstraction. You need to know a little bit about MCMC, a little bit about computation, a little bit about autodiff at this point, automatic differentiation. Hopefully that changes over time, but right now in the state of computation that is Stan, you have to know these things to get really good results. You may not have to, but oftentimes you will. And the last real big difficulty is that there are no built-in models. This is both a blessing and a curse. So there are no vetted CAN models with robust built-in regularizations and optimization and approximations. So if there is no time series model with an AR1 that works on no matter what data you give it, that just doesn't exist. You have to write that. Okay. So the last part of the talk is about why I use Stan. And quick disclaimer, this is going to be way oversimplified. There's a longer video if you want. I can send the link around. That was done by Jackie Burrows, the head of Data Generable, and a lot of this work is her work. But the video will show the use case, and I'll describe some of it. All right, so as I mentioned before, Generable, our company, uses Stan. What do we use it for? The data that we have are clinical trials in oncology. So patients have tumor scans over time. So they come in, they get imaging, and people measure the images and measure tumor sizes. So that's what you're seeing on the right side. Patients have events. Some of them observed, some of them are censored, some of them are truncated. But over time, you can see the number of people that are surviving up to, here it's 80 months. And this is simulated data here. And the goal that we have is to predict survival from early tumor data. And what does that mean? So early tumor data is, if you look at the left, it's the black dots. Ignore the predictions there for a second. So it's the black dots, and if you follow them all the way through, you'd see all the way to the non-filled dots. And here we're cutting off the sample at just under 10 months on the left patient, and the right patient is cut off at 14 months. And what you see for the survival observations, the event observations, is you only get up to time 14 months here. So this isn't a lot of data. From this, can we predict how well people are going to respond to the treatment? I'll get into the model that we use. It's a 3-part model. The first is a tumor size. So we have this is sort of like a semi-mechanistic model of tumor size. So we're going to say is that tumor size at time t, we have an estimate for the baseline tumor size, and it's going to be the sum of 2 exponentials. F is a proportion. So if F is high, then most of the cells will shrink. That's the minus Ks here as time goes on. And if F is low, we'll get more into this term, which is a regrowth term. So most of the cells will continue to multiply and get bigger. So that's a tumor size model. The second part of the model is that we created these two, I guess the best way to describe them are metrics based on the parameters of the tumor model. And they are tumor shrinkage and tumor regrowth, and they've been scaled down so that they're on the similar scale here. And what you can see is that they are sort of correlated here. And the way we use that is we associate this part, this is the association part, and we associate that with the survival model. If you're familiar with survival model, this is the hazard on the left. So at time t, there's an instantaneous amount of risk that a patient has of seeing an event. And this is a proportional hazards model. So there's a baseline hazard here. And then you're multiplied by each patient's individual other factors of risk. And in here, these are smoking status, age, line of therapy, gender. So that gets into here, but on top of that, we have information about tumor shrinkage and tumor regrowth. So the modeling assumption here is if your tumor shrinks, maybe you should have a better chance of surviving, or longer survival, less risk. All right. So how does this work? I originally showed you the observations from a phase 2, what would look like a phase 2 study. What we do is we estimate what happens in a phase 3 study. So first thing we do is we project out from 30 patients to 300. This is what would happen in a phase 3 study. That's why these lines are not exactly the same as the KM curves earlier, their earlier plot. And from that little data, we're estimating these curves for both the control and the treatment. So it works fairly well. The more data we get, the closer we are. So that's our actual use case, and there's much more to it. And so I'll conclude with, why STAN? Why do we use STAN? We have knowledge about the data generating process. We've encoded that using a tumor dynamics model with association and the survival model. The model is complicated and data is precious. Here it's clinical trials, so there just aren't an infinite number of patients that we can recruit for these trials. That requires a lot of follow-up, and when I say the model is complicated, not only is this 3-part model difficult to code, but we also have to deal with real things like truncated events, meaning we don't see the event yet, someone left the study. Censored data. There are times when the measurements don't come out in labs because it's under some sort of limit that can be detected. We know that there's something there, but we just don't know. We have to use a little bit of hierarchical structure here because there's only a few patients. Where our modeling assumptions are that certain patients are actually very similar to each other and others aren't. We end up with an interpretable model. And by interpretable here, it's longer overall survival is seen with shrinkage and tumor. That's what we're expecting, and that's what we see. And that's great. And yeah, there is no off-the-shelf package for this model. Yeah, that doesn't exist. So we had to do this on our own. The last thing I do want to mention is that we're continually learning more about the data generating process. So this is just one iteration in many of this model. Next week, next month, next year, we'll have another version and another version. And so having a tool like STAN is really good for us because we can write our models in this and continue to expand them. And that's my last slide. Thank you. That's how to reach me, and I'm happy to take questions.
Hi, thanks, Daniel, for this interesting peek under the hood for Stan. So let's go to the questions. So I see one question from Juan on Discord asking, how did you come up with the tumor size model equation? Is it a standard in the oncology field to use these exponential models, or is it something else?
That's a great question. This one is one of the more common ones in the field. Maybe not more common. There are a few that are common. There are different class of models. Some of them are what they call empirical, meaning that they just have a functional form. It's mathematic. They look at the data and they find a functional form for it. And then there are others that are mechanistic or semi-mechanistic, which describe how they believe the tumors to work. And this one's kind of a mix in between. And the sum of exponentials actually makes it so that it captures a lot of the dynamics. So a lot of patient's tumor scans over time actually fit this dynamic. Not perfectly, but it's the body is really, really complicated, and there is a modeling trade-off. We could do something much, much more complicated, and unfortunately, we don't have enough data to back that up. So we have to simplify the model to get estimates that make sense.
Okay, great. Thanks for your answer. I have another one from one of our committee members. So do you have examples when to start modeling in STAN instead of just using perhaps linear mixed effects models packages?
When to start? I think it'll come down to a, a lot of people start with Stan when they start running into hidden assumptions, not understanding what's happening with, like, if you specify a model and the solutions that you come back are not what you expect, you're now touching like either a bug, a weird property in the model, a weird property in the inference algorithm, and like a lot of people start there, coming in from that side. Uh, Other practitioners just start using Stan because they come from places where they're used to writing statistical models on their own. So I'd say, it's always good to start with toy examples, but you're really going to stick with it when you get to a point where you have to use it.
Okay, cool, thanks. And maybe last one, also tying into our next presentation. So we have someone discussing PyMC3. Could you maybe sort of give your take on the differences and why should we use Stan instead of PyMC3?
Yeah, PyMC3 is a great package. I know a lot of the people that work on it. It's the goals are slightly different. Stan was made to be Stan. Historically, we borrowed a lot of the language syntax based on bugs and JAGs. So that's the community that we started with, and so Stan is its own language. A lot of people that are Pythonic find it pretty offensive. They have to learn another language. So if you're Pythonic, I get it. Stick with Python. Stick with PyMC3. There are speed differences and there are breadth differences. Like right now, Stan, there you can do a little more with Stan. This won't be forever, right? Both languages are changing and improving. So hopefully everything gets to the same spot and you have an equal choice. But right now, for us, it's speed and flexibility.
All right. Okay. Thanks, Daniel. Thanks a lot for making the time all the way from the US, and giving this great presentation, answering all our questions. So, Daniel, if you have some time later to look at the Discord channel to see if there's any other questions coming up. And for now, yeah, thanks a lot for your time.
Yeah, I'll be on there for a few minutes. Thanks all. Bye.
Okay. Thanks.